and welcome to the McHale Report podcast. My name is John McHale, Group Editorial Director for Military Embedded Systems and host for today's podcast. This podcast is sponsored by Pentec, the leader in providing high-performance wideband and narrowband software-defined radio board, recorder, and system-level solutions. For more information about Pentec, please visit www.pentek.com/go/podcast. For more information on recording system strategies, view the Development Tactics and Techniques for Small Form Factor RF Signal Recorders white paper, which you can find at that location as well. And this podcast is also sponsored by Abaco Systems, who recognize that as a concept, C4ISR has been around for a long time. Over that time, its meaning hasn't changed. It's still about situational awareness, delivering the information warfighters need in order to make the best decisions. What's changed, though, are two things: increasingly diverse as well as increasingly numerous threats. Second, responding to those threats now demands enormous increases in computing capability. Abaco is responding by enabling C4ISR systems to acquire ever more data from sensors, process it at high speeds, and turn it into meaningful, actionable information as close to real time as possible. For more information, please go to www.abaco.com. That's ABACO.com. And now, our guest today is Sean Darcy, Director of Aerospace and Defense at Analog Devices. And today, Sean will discuss C4ISR trends and innovation at the RF and embedded electronics level. Sean, welcome. Before we get started, can you tell us a little bit about what you do at Analog Devices?
So, hey, thank you, John. I appreciate you having me on. So, here at Analog Devices, I am one of the directors here on our Aerospace and Defense business unit. So, Analog Devices is a really large company, has about 55,000 products. But what we do is we are the focus on the customer and providing customer support to the U.S., NATO, and allied Asia customers.
That gives you a feeling worldwide for a lot of the trends happening in aerospace and defense. So where do you see what are some of the biggest technical challenges the DoD needs to solve for C4ISR applications such as electronic warfare, radar, et cetera?
Well, it's a real good question. I think there's actually two challenges that are being driven by some pretty high-level requirements changes and changes in the way our doctrine, not just for physical warfare, but basically spectral warfare, has to be fought. I think one of the biggest changes is we're moving to the return of having to face a pure adversary, especially in the electronics part of the battle space. You know, we spent probably the better part of the last 15 to 20 years fighting either against rogue states, some almost third world nations, and then a lot of times against terrorist organizations. And, now we're moving back to the place that we're in competition with either near peer or peers as far as what our adversaries will look like. I think another challenge there is the peers have actually become far more sophisticated. And let me give you a couple examples of what I might mean there. If you look at like electronic warfare and the designs if you look back at the older systems designed 30, 40 years ago, a lot of times our adversaries were very high power, a very broadband, very unsophisticated type of jamming or even communications or even radar for that matter. And nowadays, they've developed their own ability to be very agile. In other words, they can jump around the spectrum very easily. They're very almost jam resistant. Their encryption has gotten a lot better, and their ability in algorithms has advanced greatly. Combined with that is people have learned the fact that there's so much noise in the spectrum this day that they can actually hide in the noise far better than they could even 10, 15 years ago. You also look at probably the biggest change is that at least two of our top adversaries or potential adversaries have also developed an ability to go much, much higher in the spectrum. If you look at the higher parts of the gigahertz and even in the 110, 120 gigahertz years ago, that was almost the sole domain of the U.S. and NATO, and now that's being challenged pretty actively. And I think there's a lot of the same changes apply to the radar space. We for a long time didn't have to worry about low observable or stealth aircraft. We've seen China, for example, bring out their first one. We see adversaries be able to make things that are low observable or attempted stealth vessels, and even some armored vehicles are being made to have very, very small radar cross sections. It's a new challenge, but one I think the U.S., NATO, and allies can easily adapt to. Something else is that their ability to do jamming and radar has become far more sophisticated. And then you look at things like swarms. And then finally, you look at command and control. There's a lot of challenge to our spectral dominance. We also, when you saw the ability of the enemy to jump around the spectrum, they've also advanced a lot about what they can do as far as jamming us. So I think it's things that people see a lot are GPS jamming, which is become a very great concern for many. But I think, on the other hand, we've developed a pretty good ability to get around that with some of the things like the new M-code GPS, et cetera.
Yeah, and you talked about cross-domain warfare, and you talked land, sea, air, but now the spectrum has become one of those key domains that we need to focus on as well, like you just described. Would you say that for years we had such a large lead in terms of technology and capability? Is that gap shrinking? Kind of sounds like it is with our adversaries. They're catching up, or we just have to be more diligent to stay ahead?
Yeah. I think, we still have an advantage. I think, though, I think you bring up a great question, a great point. I think if we were sitting in one of those adversaries, they would feel like they're pretty close to catching up. I think part of that is that, the world has moved to a very COTS mentality where now our advantage, instead of being just pure hardware, is a lot of times in software systems integration. And so I think they've closed the gap significantly. I think if you look back years ago, maybe we had a 5 to 10 year lead. I'm thinking we're about a 2 to 3 year lead now.
Well, that's we got to expand our lead, or at least keep this one.
Agreed.
Yeah. So, and how do we do that at the RF and component level? What kind of solutions can we do to enable these advantages in the C4ISR systems?
Well, I think some of the good things we do in industry, especially in the aerospace and defense industry, we look at the spectrum. We can actually play pretty strongly up in the higher, up to even like 130 gigahertz. And we've done things where we've actually not just made the converters and everything else support that, but we've actually seen some significant advances in things like GaN amplifiers, the up converters, and even the filters that support that kind of advances that still give us a hardware advantage and integration. And I think that's hard to match anywhere else in the world. I think the U.S. leads in that. I think, a lot of our NATO allies are pretty close in that. But that's it's still a really, really good, strong strength. And we have a lot of I think a lot of excellent initiatives. You look at some of the DARPA funding, some of the consortiums that are really trying to encourage U.S. semiconductor and U.S. Actually even N primes to move forward in this area. I think it's starting to pay some pretty big dividends. I think also something you see is integration. If you look at even like one of the transceivers we have, this is something that was 7, 8, 10 components across a rather large board space. And now you have, basically a very small single package, agile frequency hopping, its own internal clocking oscillator type, transceiver core. These are very, very small. And really, except for possibly needing an amplifier or other things, you actually have an entire radio in a package. I'd also say they're probably more secure because of the way they can be designed. And I think something actually that's been a real great thing across, especially when you look at like electronic warfare and some of the higher power systems is, people, at least industry and the government, I think have moved to some good standards in the module type business. And I think you've seen things like, a good example is like the 3U VPX, the 6U VPX type of standard. And these are basically standard form, fit, function interfaces, LRU, line replaceable unit looking boxes that actually can be put into a VPX chassis. And so, for example, you can have one that's a power, one can be an up converter, you could have a 16-channel ADC DAC pair, all in these standard types of cases. They almost look like a plug-and-play, PCI Express for a computer. But I think this is very, very important. It's getting us the advantage back because it's a very good enabler for speed to market. And the other thing is that if you have an existing system, you just need to only upgrade a card. It's not requiring an entire system design. So I think it makes the U.S. and allies, it gives us a lot more flexibility, and we can reconfigure or address a new threat pretty quickly.
And if you think about it, and you and I have talked about this before, the military doesn't drive innovation the way they used to. They're now a customer of commercial innovation like pretty much everybody else in the world. So the key thing is how do you embrace that? And you mentioned standards, open architectures, and 3U VPX, 6U VPX. A big thing that's happening through the government, when one of those initiatives is called the Sensor Open Systems Architecture, which is actually leveraging VPX to get more commonality on these sensor systems like we've talked about. So that's getting a lot of enthusiasm too. They're doing a lot more demos and such at different events in the industry. But taking that to a more practical level, I know you're a pilot and you flew involved with military and commercial aircraft. How does this compare now with what we're seeing in terms of this innovation for an airborne systems that might have was so much different, light years different than what you were flying back in the day? I always like that. I've been dying to ask you this question because I'm really curious.
So, it's interesting. There was a really good chart somebody put out not too long ago, and it showed the number of watts that an aircraft is required for commercial aircraft, and they contrasted basically a 737 to a 787. And I think it was something like 80 times the electricity that goes into a 787. And I think you see that a lot in the military as well. Yeah, it's a huge thing, and I think we'll be together at AOC. I'll bring the chart and show you. But it was, but I think you see that also in the amount of electronic content that's in everything in the military. You looked at the cost and the drivers of cost in an aircraft probably 30, 40 years ago. I'd be willing to bet electronics was maybe 20 to 30%. Now it probably drives as high as 50 or 60%. I think to the operator, though, when you think about it as a pilot, you're almost more of an engineer than a pilot these days. If you have a weapons officer or a WISO on board, right, you have to have a guy back there that's dealing with amazing complexity. You look at something like even, an E2D or some of the,
the
early warning rate. Yeah, the early warning, or even some of the, the guardrail or something like that, where you're actually flying, reconnaissance and sniffing the spectrum. The systems on board are probably probably 2 orders of magnitude more complex than were even 15 years ago. And you think about even something like the C-12 guardrail, which is not, a big, glorious airplane, but it has an amazing amount of mission capability put in what really is a pretty small airframe. And so I think the thing is it's starting to drive, at times almost a data overload. And it's a good challenge for us to have because it means we still have the advantage of being able to collect all that information. But I think it's going to drive probably a new way of thinking about the way we manage basically battle space and spectrum information in airborne systems. So.
And the changes happen even faster every year than it did. Maybe the pace of change happens more quickly.
No,
speaking of AOC, which stands for, you mentioned that earlier, that event next week, that's the Association of Old Crows, and it's held every year. For those of you who don't know, Old Crows means retired admirals. But essentially it's a nonprofit Association of Old Crows. They put together an event every year. That's one of the best of its kind where they showcase technology solutions for electronic warfare, radar, signal intelligence, and other ISR applications. And that's happening in Washington, D.C. next week. I know Sean's going to be there. I'm going to be there. What do you see are some of the trends that you think might emerge at the event this year? And we've talked in the past there about, increased leverage of artificial intelligence. There's always reduced swap requirements. What do you see possibly emerging next week?
Yeah, AOC is a great event, and I'm honored to attend again this year. And like you said, we'll have a booth there for analog devices. Please come visit. But I think there's a couple real big changes and challenges I've seen just over probably the last 18 and 24 months. And it's kind of interesting. You brought up something I'd like to touch on is first is you think about the amount of raw data systems can now collect. And, that this is driven over time, these needs for these really high performance, but really flexible, high speed converter components and some of the related designs that go with them. And, it's not just the ability to have greater bandwidth, right? We're driving up higher and higher in the spectrum to track not just adversaries, but sometimes it's even, you have to go look at you may actually have to be in a country and start looking for certain civilian communications and things like that. Even those have become much more complex. But it drives something that's kind of interesting, which actually is kind of the second problem. Besides trying to figure out and track all that huge, broad new spectrum that we have available to us, the big second thing is how do you move all that into a digital data domain? And one of the things that a couple programs I worked on years back is that you could build these huge digital sampling or direct sampling systems, and the problem is you just buried your gigabit or even 10 gigabit or 100 gigabit backbone. And so I think one of the things we're going to see, and I'm guessing we'll see some more people talk about this probably at AOC this year and next year, is how you actually do better digital decimation. And I expect to see some more smarts and that ability to actually to basically do some processing and reduce big data streams down to the actual core components that are of interest for both ways, both for ADCs and DACs. I expect that to get closer and closer to the antenna as the years go on because we just can't put that data onto the backbone fast enough. But you asked about AI, and I think there's going to be some interesting keys that I have probably a different view of that than others. A lot of people have been looking at AI for some things about signatures and identifications and things like that, and I think that'll keep happening. But I think one of the things we're really going to need is that we're going to need actually not expert systems, but really self-learning systems that know how to look at either a new or existing spectrum that we don't have everything identified, we don't have a baseline on, and be able to use self-learning algorithms to identify and then track either threats or blue force.
Is that cognitive EW? Is that the cognitive EW that we read about sometimes?
Yes, it definitely is, definitely. And I think that's going to have to advance because no mission operator on a council can deal with that amount of data, even with all these filters and everything else that helps them do that. The thing is that they're hard programmed, and the threat or the signature is hard programmed. If it changes, he may not have the bandwidth as a human being to find that. So I think we do need these big cognitive systems. I think another thing is interesting is a good example is when you have, if you're looking out across the spectrum and you're real broadband, right? You know, pretend that we actually have hardware that can go from 0.3 gigahertz to 130. You know, how does a human being actually see a threat pip up here and there and actually quickly focus and start to signature it? I don't think it's something you can pre-program as much as you have to have some type of learning system that does that. And then finally, I'll tell you that this one goes back to what I said before about data. I think we're going to see more and more people have to find either better ways to do pure analog or some type of expert learning system on the backside to actually figure out where do we put all that data. And I always say if you think about the amount of data that one single 8 gigasample per second converter can generate, and you look at something like a phased array, it has just a simple one with 100 converters on it, it's a massive amount of data we can store. And if you're going across the spectrum, we're going to have to find ways to actually turn that into something that a computer can actually comb through looking for something significant, but also a way that a human being can look at and have some understanding and make some good command and control decisions. So I think that's going to be a big challenge.
Yeah, and it's not just figuring out how to, because the bandwidth's kind of hard. You don't have as much you can deal with in getting just that data transfer down. It's where they're putting so much processing power at the sensor level. But what you're talking about is you got to store all this stuff somewhere and then filter it. So there's two challenges there. Okay. And hopefully we'll see, definitely. I'm sure we'll see some solutions about that next week, people talking about that on the floor. And that brings us to our time limit for today. But thanks for speaking today, Sean. Always good to catch up. Look forward to seeing you next week. You want to provide a website on how listeners can learn more about analog devices?
Sure, yeah. If you can visit us, we're at www.analog.com. So it's analog.com. And we'll definitely be at AOC and look forward to seeing people there. And thank you, John. Thank
you. And I'd also like to thank our sponsors today, Pentec, the leader in providing high-performance wideband and narrowband software-defined radio board, recorder, and system-level solutions. For more information about Pentec, go to www.pentec.com, pentek.com/go/podcast. And there you can also find out more information about their recording system strategies by viewing the white paper, Development Tactics and Techniques for Small Form Factor RF Signal Recorders. This podcast is also sponsored by Abaco Systems, who recognize that as a concept, C4ISR has been around for a long time. Over that time, its meaning hasn't changed. It's still about situational awareness, delivering the information warfighters need in order to make the best decisions. What's changed, though, are two things: increasingly diverse as well as increasingly numerous threats. Second, responding to those threats now demands enormous increases in computing capability. Abaco is responding by enabling C4ISR systems to acquire ever more data from sensors, process it at high speeds, and turn it into meaningful, actionable information in as close to real-time as possible. For more information, please go to www.abaco.com. That's ABACO.com. And thank all of you for listening to today's McHale Report podcast. Look forward to seeing you on a future one. Take care.